This next section we're going to be looking at a new method for solving systems of equations. We're going to be using a technique called matrices. And basically matrices we're going to be able to utilize them by hand and using our calculators. And so if you have your calculators available, you're going to want to get them out. Okay, we're going to be utilizing these things probably more than doing them by hand, but I want you to get the idea of doing them by hand before we get into the calculator, so you see kind of what's going on behind the scenes. So to motivate this, I want to do a quick review of elimination method. This is what we talked about in the last section, and this example was the first example that we looked at in that last section. When we did the elimination method with this, we added the two equations together to eliminate the y variable. Okay, so I'm just going to run through this very quickly so you can see how this develops and how the matrix idea works out of this. So we're going to first add up the equations just like we did before. X and 2x makes 3x. The y's drop out, and 5 and -8 make -3. Then we can divide both sides by the 3, and we get an answer for x of -1. Then we went and substituted that -1 back into one of the two equations, didn't matter which one. We could do the first equation, x plus 3y equals 5. We plug in the -1 for the x value. Then we can add 1 to both sides. We get 3y equals 6. Then we can divide out the 3 on both sides. Doing quite a few little colors here. And we get 6 over 3 is equal to 2. Right, so x equals -1, y equals 2, and of course our final solution needs to be in needs to be the ordered pair in a solution set. Okay, so the answer we found, and this is consistent with what we had before, is -1, 2. Now the reason I'm showing you this example with elimination is because the matrix idea, what we're going to do, builds off of this, is actually kind of a shorthand way of doing this. The key here is to get the concept that your answers, the -1 and the 2, are simply combinations of the original 4 coefficients and 2 constants. Okay, so if you think about this, the -1 comes about by adding the 1 and the 2 coefficients to get 3, adding the 5 and the -8 to get -3, and then dividing the -3 by this 3. So dividing the two differences. Okay, and so this number is simply a combination of the 6 numbers that appear in the original system. Had we solved for y first, we could have multiplied through this by a -2 to drop out the x's, solve for y. We would have been able to find the value of 2 instead of -1 would have come out first, and it also would have just been a combination of these 6 numbers. Okay, and so the main idea here is that we can sort of shorten up the elimination method by simply writing out those 6 numbers in what we call a matrix. Okay, so a matrix is basically a rectangular arrangement of numbers into rows and columns. Okay, And so in our case, the matrix that would represent this system would be to just pull off the coefficients 1, 3, and the constant 5, and then 2, -3, and -8, and write them in rows and columns, keeping the rows consistent with each equation and the columns consistent with each variable and constant. Okay? So the matrix then for this particular system would be 1, 3, 5, and 2, -3, -8. We put square brackets around the matrix, probably just so it looks like a rectangle. It's just our common notation. We also tend to separate off the two sides of the equation by putting a vertical bar where the equal signs would go. Any matrix then that represents a system of equations is what we call an augmented matrix. Okay, so an augmented matrix represents a system of equations. Now perhaps the definition is slightly different from that, but that's really what we need to move forward. Okay, so that's the system of equations in matrix form. Now, the final answer, which is kind of interesting, is also a system of equations. Okay, you could kind of think of it that way anyway. Take a look at this. If we look at x equal -1 and y equals 2, that is essentially a system, and if you think about filling in all the details here, that is essentially the system 1x plus 0y equals -1, and this has 0x's, 1y equaling 2. Okay, and so you're actually looking at another system of equations just in a shorthand form, and we can pull the answer out of the right side of that system. This new system is what we call a reduced form. Okay, in fact, if we turn it back into a matrix, this system would look like 1, 0, -1, 0, 1, 2. Put the rest of our notation in there. And now we have a reduced matrix. What's interesting about the reduced matrix is that there are 1s on the top left, bottom right, and 0s elsewhere. Okay, what we'll find is that a matrix in this form will always have the solution on the right side. Okay, so the question is, how do we get from this initial matrix to this final matrix so that we can pull out the answer? Okay, and the answer to that question is utilizing principles of equality in the same sort of way that we use the elimination method here. Right, we discussed this last time, that the elimination method, essentially you're adding the same amount to both sides of this equation. When you add the equations together, because the two sides are equal to each other, we're adding the same amount to both sides of that first equation. You can also utilize the multiplication principle. We did this in other examples when you had to multiply all the terms by a number. And then you can also do some other weird things that are just kind of useful, like switch the two equations around. Right? You could switch them around, you get the same system, the same solution. It doesn't matter the order in which they appear. Okay? And so we have what we call row operations. They're things that we can do to the rows, which really represent equations, that don't change the solution to the system. Okay, one of those row operations, we'll call them, actually they're given a name. They're called the elementary row operations. And I'm going to write them out here. The first one is that we can interchange rows. That can be a useful little trick. We don't see it very often when we're doing the elimination method because the order of the rows is arbitrary, but here it can be useful to try to get this pattern on the left side. Another thing is you can multiply a row by a constant, multiply or divide by a constant. So multiply or divide a row by a constant. We saw that during the elimination method, not in this particular example, but again I said when you multiplied each term by a number in order to get the least common multiple of the coefficients to add out. So we saw that before. And then the third type of elementary row operation is to add a multiple of one row to another. Okay, so add a multiple of one row to another. That's essentially what we do in the elimination method, is you multiply a row by a number and then add it to another row to get a new row. Here I didn't have to do the multiplication step. I just added the two rows together to get a new row or a new equation. So every time you get a new row, you get a new equation that still has the same solution as the original system. Okay. Now the last thing I want to do in this video is just define or give a definition for this final form. We're going to call it the reduced row echelon form. Okay, also known as RREF.